So for our bead design challenge, our customer was an elderly person who wants to sit down and has back and joint pain that got dropped off at the beginning of the parade route that needs to be able to take breaks throughout their walk. So then with our objective tree, it starts with our first idea being the bead thrower, and then the first subscript is the probability, and then that breaks into three more, which is how small can it be light, and can it be comfortable? And then those break up into, can it be maneuverable, balanced, and be able to fit nicely while carrying? And then the other subscript is safety, and this splits into two, which goes to user safety and audience safety. And then those two split into, does it fail under stress, and it can't be too annoying to use. And then the last script would be cost effective. And this splits into two more, which would be reliable and cheap. And then these split into two more also, being easy to fix and then cheap to maintain. So with our house of quality, we have functions and constraints. Under the function section, we have comfort, cost, safety, and efficiency. And under the constraints, we have how many beads per minute can it throw, the total device weight, the mechanism tolerance for it to be able to work properly, the reload time, and the velocity of how fast the beads will be moving out of the muzzle. And then for our relationships, everything fell under moderate and strong. First, with being comfort and beads per minute, that fell under moderate. And then comfort and device weight, that fell under strong. And then comfort and feeding mechanism tolerance fell under weak, actually. And then comfort and reloading cycle fell under weak again. And then comfort and muzzle velocity fell under medium. And then cost and beads per minute fell under strong. Cost and total weight fell under medium. Cost and feeding mechanism fell under medium. Cost and reload cycle time fell under medium. Cost and muzzle velocity also fell under medium. Safety and beads per minute fell under the strong side. Safety and total device weight fell under strong. Safety and feeding mechanism fell under strong. Reload time and safety fell under strong. And safety and muzzle velocity fell under strong. Efficiency and beads per minute fell under strong. Efficiency and total device weight fell under strong. And efficiency and feeding mechanism tolerance fell under strong. Efficiency and reload time fell under strong. And efficiency and muzzle velocity also fell under strong. And for our morph chart, we had 4 sections: handheld, low profile, can't hurt anybody, and cost effective. And for a decision matrix, we had 5 criteria and 3 concepts. The first criteria was to decrease energy being used from the beads being thrown. The second one is can stand the use throughout the whole parade. And the third one would be easy for the crowd to catch the beads. The fourth one would be just easy to use. And the last one would be to easy to fix. And our 3 concepts was a claw thrower. Our second concept was a bead launcher. And then our third concept was a crank thrower. And overall, the concept that won was concept 2.
So when we started thinking up a design for the bead launcher, this is kind of what we came up with. We have the grip right here with the trigger, and the trigger would push up on this end of the lever, which would push down on this end. And the bead pusher plate, which is this piece right here, would be pushed forward by the spring, and the beads would be launched out. And when we were trying to figure out how big we wanted the barrel to actually be, we just drew some circles to scale. As you can see, the radius right here is 6 centimeters, radius right here is 5.5. And then we would just pile beads on top. So as you could see, a big bead, when laid in that 6 centimeter radius circle, was about 8 centimeters high. And in the 5.5 centimeter barrel, it was 9 centimeters high. And that would basically tell us, how many beads we could fit in the actual launcher itself when it was fully loaded, so that we knew an estimate of what the payload would be. Now, in terms of actually designing it, we started off with the barrel, which was, as you see, just a circle that was extruded, and then we cut out a part in the center, and we have these channels right here, as these two on the side and the one on the top, that would guide the bead pusher plate and prevent it from rotating or going up and down or side to side in ways we didn't want it to. And the reason why this one at the top right here is open and the ones on the side aren't is because the bead pusher plate actually pokes up a little bit higher than the outside of the barrel so that you could tell whether or not it was loaded, so you didn't actually have to look down the barrel of it to see how far back the bead pusher plate was to signify whether or not it was loaded. And then at the bottom here, we have four little pegs that would help you align the grip, and then this is where the pin would go through that holds back the bead pusher plate, and then the end plate is what the spring pushes on to push the bead pusher plate forward, and it slots in through these four circles here, and then it to make sure it isn't forced out on the back, we have pins right here that would lock it in place. So this is what the end cap looks like. We have this circle right here that is, as you can see, extruded out that the spring sits around the outside of. And then we have, as you can see, these are the pegs that slot into these holes. And if you note, the holes right here from earlier line up with these holes, and you get some end cap pins like this that would actually slide into those and keep it in place. And then this right here, make sure that whenever you're cocking back the bead launcher, you don't push it too far and potentially damage the spring. And this would push against the back of the bead pusher plate, which is this right here. And you can see we have these two little arms that fit into the slots of the barrel on the side. And then this top one that slots through here. And then we have where the front end of the spring would go, which is to make sure that it doesn't, mount up here or down here. And then at the bottom, we have uh, where the pin, like I mentioned earlier, the pin slots up into the barrel and it would sit in this little slot right here to hold back the bead pusher plate. So this is the spool, and basically this is what would cock back the bead launcher. So there's a little motor that attaches in this little spot right here, and it'll spin up the spool as the person is walking, and that will pull back on the bead pusher plate, which will have a string going through this little hole right here, and then will be strapped around a little pin that sits sideways in here, and that will pull this bead pusher plate back. As for the grip, I just took a 3D print file off of a website or just on the internet. It was a free file of a Nerf gun foregrip, and I just cut off a circular bit at the top right here so that it would sit up nicely against the barrel. And then we have a hole for the pin and two more little holes to fit some foam in here so that the pin would have something to push up against or push up against it to push it up into the bead pusher plate. So this right here is the trigger pin, like I was talking about earlier. This little hole right here is where the string would go through and it would tie it, and then you could pull the string from the bottom of the handle. And the reason why it is sloped at the top is so that when you're actually cocking back the bead launcher, if this was just flat, then it would just try to snap this in half. But since it is slanted, it would actually push it down against the foam, and then once it clears, it would push back up. So in terms of what it looks like as an assembly, as you can see, this is it all together. You have the bead pusher plate right here, the grip, the barrel, the rear end cap, and this is the spool sticking out of the back. So if we remove, let's see, we can remove these pins. Uh, and rotate it like this. We can pull this end cap off, and you can see the assembly right here. The spool sits in the middle of the end cap, and then let's see. And then as you can see, these pins fit into those little pegs right there. So just going to move this back out. And then if we turn on sectional analysis, you can see the bead pusher plate is free to move in here. And if we bring this back, why does it not? There we go. Just a little buggy sometimes. And then as you can see, the bead pin or the trigger pin slots up, and as this moves back, it pushes it out of the way, and this will load for a second. The phone will push the pin back up and prevent it from moving forward. Obviously, Fusion's physics aren't the greatest, so it does just knock it out because it's easier to calculate it or whatever. But yeah, that's the basics of how the bead launcher works. So in terms of what the launcher actually looks like, for harvesting the energy, we have what would be motors connected to wagon wheels. So as you spin the wheels, it charges this battery pack, which would then give you a steady power output to this motor here. So see, I turn on the switch and the motor starts spinning. And the motor would slot into the back of the bead launcher here. As you can see, there's this little hex bit right here where the motor slots into. Flip on the switch, and as you can see, it is turning the spool, and it would be pulling back the bead pusher plate. However, there was a lot of stuff that went wrong in the 3D printing, and the actual barrel itself, this white piece, and the end plate uh, weren't actually printed at the same size because they was on two different printers, and I guess their interpretation of a millimeter was different. So as you can see, there's this little lip right here that isn't supposed to be here. That wasn't there in CAD. Everything lined up in CAD. So all of the mounting holes that were supposed to line up didn't line up. You can see that's the little slot where the peg was supposed to be. And yeah, it if we had known that the 3D printing was going to mess up like that, we would have done it on one printer and it would have ended up turning out a lot better. So if there was one thing we could do different to improve, it would be to print it all on one printer, or at least on printers that had the same interpretation of a millimeter, so that everything would come out lining up perfectly.